Every single day, factories produce thousands of pounds of bubblegum using a process so intense and fast, it looks more like industrial science than candy making. Behind the bright colors and sweet flavors is a production line powered by heat, pressure, and machines built to run non-stop. In this documentary, we take you inside the world of large-scale bubblegum manufacturing to see exactly how this chewy favorite is made from start to finish. Historically, gum base was made from natural tree resins like chicle, a latex-like substance harvested from the sapodilla tree, which grows in Central America. However, nearly all modern bubblegum factories now rely on synthetic gum bases. These are specially formulated blends of food-grade elastomers, resins, waxes, plasticizers, and softening agents. The use of synthetics provides far greater control over consistency, shelf life, and bubble blowing capability, which is critical for mass production and distribution. The raw materials used in synthetic gum base are delivered to the factory in large sacks or drums, and each ingredient is sampled and tested before entering the production line. Elastomers such as polyisobutylene and polyvinyl acetate provide the stretchy, elastic properties needed for bubble blowing. Resins act as binders that hold the gum together. Waxes like paraffin and microcrystalline waxes are added to soften the mixture and give the gum its pliable, non-brittle chew. Plasticizers such as glycerol, esters improve texture, while fillers like calcium carbonate or talc give the gum body and density. Each of these materials must be prepared for mixing. Solid components are broken down using industrial grinders and micronizers to achieve a uniform particle size, which ensures even distribution throughout the base. Waxes and resins are often pre-melted in jacketed stainless steel tanks equipped with indirect heating systems to prevent scorching. The raw elastomers are delivered in dense, rubbery blocks that are cut down using industrial dicing equipment before being added to the mix. Accuracy in measuring each component is vital. The slightest deviation in the amount of resin or wax can drastically alter the final chewiness and bubble forming capability of the gum. Now it's time for the blending of the gum base, which happens in large Sigma blade mixers, named for their two interlocking Z-shaped blades that rotate in opposite directions to fold and knead heavy materials. These mixers are specifically designed to handle high viscosity compounds like gum base. The various pre-measured ingredients are added to the mixer in a specific sequence. First, the elastomers are introduced and given time to soften and break down under shear force. As they begin to form a uniform mass, resins are added to bind the structure. Waxes and plasticizers follow, blending smoothly into the mixture to help reduce internal friction and improve processability. This mixing process is not quick. Depending on the size of the batch and the recipe, the blending cycle can last anywhere from 45 minutes to several hours. The mixer itself is equipped with internal thermocouples to continuously monitor the temperature of the mass, which is maintained between 60 degrees Celsius and 90 degrees Celsius. Too low and the materials won't melt and blend. Too high and thermal degradation could occur, affecting the safety and performance of the gum. Operators observe the process through viewing ports and rely on torque readings and viscosity data from the mixer's internal sensors to determine the exact moment the gum base is fully homogenized. Once the gum base has reached the correct consistency, it is discharged from the mixer. This is a challenging step because the base at this point is extremely thick, sticky, and hot. To facilitate removal, the bottom of the mixer opens hydraulically and the heavy base is dropped onto a large stainless steel cooling table or fed directly into a sheeting system. The cooling table is actively temperature controlled using circulating chilled water to begin lowering the temperature of the gum base as quickly and evenly as possible. Large Teflon-coated rollers may be used to flatten the mass slightly, increasing surface area and speeding up the cooling process. The goal at this point is not to bring the base down to room temperature entirely, but to reduce its temperature to a workable range, usually between 40 degrees Celsius and 50 degrees Celsius, so it can move to the next stage without sticking to equipment or losing its plasticity. The partially cooled gum base is then cut into manageable blocks using high lubricity heated cutting blades. These blocks are weighed, labeled with batch numbers, and either sent directly to the next phase of production or stored in temperature-controlled holding rooms for later use. Even in this early stage of production, quality control is already an active part of the process. Samples of gum base are collected from each batch and taken to the plant's in-house laboratory, where technicians test them for elasticity, tensile strength, softness, and melt behavior. Specialized equipment such as rheometers, durometers, and texture analyzers are used to measure mechanical properties under simulated chewing conditions. This ensures that the gum base will respond correctly when blended with sweeteners, flavors, and colors in the next stages of processing. It's also worth noting that not all gum base formulations are the same. For bubblegum specifically, the formulation includes higher levels of elastomers and plasticizers than in chewing gum intended for long-lasting flavor or dental benefits. Bubblegum is designed to be more pliable and capable of trapping air, so it can form large bubbles without breaking too easily. This performance requirement influences everything from ingredient selection to mixer settings and even downstream cooling methods. Therefore, each variation of gum base may require its own unique process settings and equipment parameters. In the next stage, the base will be transferred into another high-capacity mixer, this time designed to handle not only dense material, but also sensitive flavor components and volatile sweeteners. The balance of heat, pressure, timing, and sequencing here is critical. Too much heat can break down sugar molecules and destroy flavor integrity. Too little, and the gum won't mix properly. The entire system must operate like a symphony of mechanical precision and food engineering science to ensure that every piece of bubblegum delivers the iconic chew and flavor burst that consumers expect. With the gum base now fully prepared, cooled, and tested, it's time for one of the most critical stages in bubblegum manufacturing: the integration of sweeteners, softeners, and flavorings. This is where the bland, rubbery core transforms into something enjoyable and familiar. The sweet, fruity, chewy product capable of inflating into perfect pink bubbles. At this point, the gum base is still a nondescript mass, pliable, tacky, but utterly flavorless and unappealing. The magic is about to happen in an industrial mixing process that must blend these next components evenly while preserving the precise texture and chew required for successful bubblegum performance. Before anything is added to the gum base, it must be brought back to a specific working temperature. Though the blocks were cooled after being discharged from the original base mixer, they must now be re-softened for further blending. This is accomplished using a series of jacketed holding vessels or warming conveyors that apply gentle, indirect heat, usually via hot water or steam circulating through double-walled stainless steel pipes. The temperature is carefully raised to a range of 40 degrees Celsius to 60 degrees Celsius, just enough to make the gum base pliable again without overheating or causing degradation of any of the soon-to-be added ingredients. The re-softened gum base is then introduced into a second type of mixer, often a horizontal batch mixer or a planetary mixer specifically engineered to process high-viscosity food materials. These mixers are outfitted with double sigma blades or paddle arms capable of kneading the gum base with immense force. Once the gum base begins to rotate and fold, the sweeteners are added gradually. These include powdered sugar, also known as icing sugar, glucose syrup, and sometimes corn syrup solids. Each of these sweeteners serves multiple purposes. Powdered sugar provides bulk, texture, and long-lasting sweetness. Glucose syrup contributes a softer mouthfeel and prevents crystallization. Corn syrup solids help maintain chewiness and shelf stability. In some formulations, especially those designed for sugar-free bubblegum, bulk sweeteners such as sorbitol, xylitol, or mannitol are used in place of sugar. These polyols require different handling due to their moisture absorption characteristics and sensitivity to heat. In any case, each type of sweetener must be fed into the mixer in stages, allowing the gum base to fully absorb and integrate the new material before more is added. This prevents clumping and ensures that the resulting mixture remains smooth and pliable. Industrial-scale screw feeders or vacuum conveyors may be used to introduce these ingredients directly into the sealed mixing chamber to maintain cleanliness and prevent contamination. Following sweetener addition, softeners such as glycerin and vegetable oils are introduced. These materials are essential to prevent the gum from becoming brittle over time and to give it the desirable, soft, elastic texture that bubblegum is known for. The quantity and timing of softener addition are precisely calculated. Too little and the gum will harden quickly after production. Too much and it will become greasy and sticky, especially under warm storage conditions. Glycerin, in particular, helps trap moisture within the matrix of the gum and acts as a plasticizer, allowing the final product to retain its chew even after prolonged shelf life. Once the bulk of sweeteners and softeners are integrated, it's time for one of the most delicate and carefully timed steps in the entire production line: the addition of flavorings and colors. Flavor compounds used in bubblegum are typically a blend of fruit, esters, vanillin, and long-lasting artificial flavors engineered specifically for gum applications. These flavors must be oil-soluble and thermally stable, as any degradation can result in bitterness, loss of intensity, or altered taste profiles. The most iconic bubblegum flavor is a blend of banana, cherry, cinnamon, clove, and wintergreen, artfully balanced to create that familiar pink taste that people associate with classic bubblegum. These flavoring compounds are often concentrated liquids or emulsified pastes, and they're introduced in the final stages of mixing to preserve their volatile aroma compounds. If added too early, the heat and shear of the mixer could evaporate or chemically alter them. The flavors are poured in slowly while the mixer runs at a reduced speed, allowing gentle incorporation. Some manufacturers use pre-encapsulated flavor beads that dissolve slowly during chewing, extending flavor release over time. Coloring agents are added simultaneously or immediately after. These are usually food-grade dyes, such as Red 3 or Red 40, depending on regional regulations, and are added in liquid form or as pre-dispersed powders. These colorants are not just about visual appeal, they help consumers identify and associate flavor with appearance. For classic bubblegum, the universal hue is a bright bubblegum pink. The dye must be evenly distributed throughout the batch, and to do this effectively, the mixer must achieve total homogeneity without overworking the gum or exposing it to heat that could cause the color to fade or change. During this final blending stage, the entire gum mass is constantly monitored. Operators inspect the mixture for uniformity, gloss, elasticity, and color consistency. Samples may be extracted from the mixer at regular intervals and manually kneaded or stretched to ensure no streaking or spotting. Texture and pliability are tested by compressing and stretching a small piece by hand or using mechanical texture analyzers. If any inconsistency is found, whether it's too stiff, too soft, uneven in color, or lacking in flavor, the batch may be reprocessed or scrapped entirely, depending on the deviation severity. Once the gum reaches the desired final formulation, it's discharged from the mixer onto a temperature-controlled rolling table. At this stage, the gum has taken on its familiar look and feel: soft, elastic, vibrantly colored, and bursting with aroma. However, it's still a massive block of uncut material, far from the small, uniform pieces sold in stores. To prepare it for shaping and portioning, the gum is flattened using motorized rollers that compress it into thick sheets. These rollers are heated just slightly, enough to keep the gum pliable, but not so hot that it becomes sticky or begins to sag. The sheeted gum is then conveyed into a sizing line, where it passes through multiple sets of progressively narrower rollers to reduce the sheet thickness to the exact target for the final product. Whether the gum will be cut into strips, rolled into tape, molded into spheres, or formed into pillow-style pieces depends on the final product format. The sheet thickness must be precise, too thick, and the gum will be too large to chew comfortably. Too thin, and it will tear or lack substance. Precision slitter blades then slice the gum into long ribbons, which are cooled again on conveyor belts using ambient air or chilled tunnels. These ribbons are stacked and allowed to rest briefly in temperature, dent, and humidity-controlled zones. This rest period, sometimes called the conditioning phase, allows moisture and elasticity to equilibrate across the entire piece of gum. It helps stabilize the internal structure and prepare the gum for cutting, shaping, and packaging without causing cracking or deformation. At this point, bubblegum is fully formed in its raw shape, but still unwrapped and unpackaged. The product is ready for the next phase, which involves high-speed forming machines, wrapping systems, and final packaging lines designed to handle thousands of pieces per minute. These systems require their own precise engineering and synchronization to maintain the integrity and appeal of the final product. Now that the bubblegum has been properly flavored, colored, sheeted, and rested, it enters one of the most mechanically intricate and visually satisfying stages of production: shaping and cutting. At this point, the gum exists in long, flat ribbons of pliable, glossy material, carefully rolled and stacked in conditioned zones to ensure uniformity and stability. These ribbons are conveyed in single file onto a forming line that uses high-speed, synchronized mechanisms to turn raw sheets into the iconic forms consumers recognize, whether small pillow-style pieces, sticks, chunks, tape rolls, gumballs, or extruded logs. Let's first explore the most common format, the pillow-shaped bubblegum piece. This format is familiar from vending machines, Halloween candy mixes, and individual wrappers. To achieve this, the bubblegum ribbon is fed into a forming wheel, where it is gently guided through a series of progressive molds or cavity rollers. These rollers are designed with alternating male and female cavities that press into the gum from both sides, creating the shape of a small rectangular block with softened edges. As the ribbon passes through these molds, the gum is compressed and cut simultaneously by a synchronized die cutter positioned just after the final molding wheel. Cutting must be done with extreme precision, as even a millimeter of deviation could affect packaging alignment and product weight. To account for thermal expansion and gum elasticity, the cutting blades are adjustable in both depth and cycle timing. High-speed optical sensors detect the flow rate of the gum ribbon, feeding data into a digital controller that dynamically calibrates the cutter's speed in real time. The gum, now formed into uniform bite-sized pieces, is ejected onto a short conveyor, ready for wrapping. In the case of bubblegum stick formats, like the flat rectangular pieces found in classic packs, the shaping process is slightly different. Instead of molding with rollers, the gum sheets are trimmed on all four edges to create clean, sharp lines. They are then passed through a rotary cutter equipped with hardened steel blades, slicing the sheet into strips of exact dimensions. These strips are stacked and cut again to create individual sticks. The machines responsible for this operation resemble guillotines, but with servo-controlled precision that allows for continuous, non-stop operation at high speeds. The final sticks are conveyed into wrapping units without any manual handling, preserving hygiene and maintaining throughput. Bubblegum tape, a novelty format often rolled into small plastic canisters, requires its own unique process. The sheeted gum is passed through a winding station where it is gently rolled into a flat coil, not unlike a roll of tape. Tension is carefully controlled here, too much pressure, and the coil will deform or stick to itself. Too little, and it will unravel inside the container. Once coiled, the tape is automatically dropped into a custom-formed plastic shell, usually hinged with a pop-top lid. A blade inside the lid allows consumers to tear off a desired length. These plastic cases are injection molded on-site or sourced in bulk and fed into the filling line by vibratory bowl feeders. For gumballs or spherical bubblegum formats, the production method is even more specialized. Instead of being formed from ribbons, these are made using extrusion and spheronization techniques. Warm gum is extruded through a nozzle into a thick rope, which is then cut into small segments by a rotating knife. These segments are dropped into rotating pans, lined with friction-inducing surfaces that tumble the gum continuously, rounding the pieces into spheres through centrifugal motion. Once the balls reach a near-perfect shape, they are cooled and coated in a separate process, which we'll explore shortly. Regardless of the final shape, all bubblegum formats at this stage are unwrapped and uncoated, meaning they are vulnerable to sticking, moisture absorption, and contamination. Therefore, the next critical phase is the wrapping and packaging process, which combines high-speed automation, material engineering, and branding considerations. Starting with pillow pieces and sticks, the gum is immediately conveyed into primary wrapping machines. These are high-speed horizontal or vertical flow wrappers, capable of wrapping hundreds of pieces per minute. A continuous roll of printed film, typically made of polypropylene or foil-backed paper, is unwound and fed through the machine. As the gum pieces travel along a conveyor, the film wraps around each piece and is sealed using heated crimpers that create a back fin seal and two end seals. For some classic styles, twist wrapping machines are used instead, which pinch both ends of a small rectangular wrapper and twist them tightly around the gum. These machines are equipped with sensors that detect gum position and length, ensuring perfect alignment between the product and its printed branding. If even a single wrapper is misaligned or improperly sealed, that piece is ejected from the line via pneumatic diverters. Wrapped pieces are then collected, counted, and transferred in bulk to secondary packaging machines. Secondary packaging is where individual units are grouped for retail sale. For stick gum, this may involve stacking 5 or 10 wrapped sticks into a flat paperboard sleeve, then shrink wrapping the pack. For pillow gum, machines automatically count the desired number of pieces and drop them into a pre-formed bag, which is then sealed using heat or ultrasonic welders. Packaging films are chosen for durability, oxygen resistance, and visual appeal, and often include tear notches or resealable zippers for convenience. In the case of bubblegum tape, filled plastic canisters are labeled and moved through a shrink sleeve applicator, which places a heat shrink label around the container. This sleeve serves both branding and tamper-evident functions, and is tightened using a controlled burst of steam or radiant heat. Finally, canisters are packed into display boxes or larger cartons using robotic pick-and-place arms. Now we return to gumballs, which undergo a unique finishing step: sugar coating. Unlike other formats, gumballs are coated in a hard, shiny shell that not only protects the gum inside, but also adds flavor, color, and gloss. This process is performed in large, stainless steel coating pans that slowly tumble the gumballs while successive layers of syrup and powdered sugar are applied. The syrup typically contains water, glucose, and food coloring, which adheres to the surface of each gumball. Then a layer of sugar or sugar alcohol-based powder is sprinkled over the syrup, sticking to it and gradually building up a thick shell. Each coating layer must be dried before the next is added. Warm air is blown gently into the pans while the gumballs tumble, ensuring even drying without cracking or warping the shell. After multiple layers are built up, sometimes more than a dozen, the gumballs are ready for polishing. This final step involves applying a thin layer of food-grade wax or shellac to the gumballs to create the glossy, reflective finish that's so iconic. The polished gumballs are then cooled, inspected, and fed into bulk bagging or capsule dispensing systems depending on their final use. Throughout the forming, wrapping, and packaging process, real-time quality control continues at every junction. Vision inspection systems verify wrapper alignment, seal integrity, and color consistency. High-speed check weighers ensure that every package contains the correct number of pieces and meets the stated weight. Metal detectors and X-ray systems scan for any foreign particles or processing defects. If a flaw is detected, the package is automatically ejected and flagged for review. And behind all of this automation is a digital infrastructure tracking every batch, from base production through to final packaging. Every piece of bubblegum can be traced back to the exact shift, mixer, raw ingredient lot, and even the machine operator responsible for that run. This traceability system is essential for food safety, quality assurance, and regulatory compliance. Once bubblegum has been fully processed, formed, wrapped, and inspected, it enters the final phase within the factory: storage, quality verification, and preparation for shipment. Although the gum is now finished, it still requires careful handling to ensure that its quality and integrity remain intact all the way through to its final retail destination. The post-production environment is just as controlled as the manufacturing zones. Finished goods are transferred into climate-regulated storage areas, where temperature and humidity are strictly maintained to preserve the texture, flavor, and packaging condition of the gum. Each product pallet is labeled with QR codes or barcodes that carry essential traceability information: product type, batch number, production date, and expiration code. These codes integrate with warehouse management systems that organize inventory by shelf life and destination. The warehouse operates on a strict first in, first out (FIFO) system to make sure the oldest products are shipped first, reducing waste and ensuring consistent freshness in the marketplace. Before any product is released for shipping, quality control teams perform final checks. Samples from each lot are pulled and tested for packaging seal integrity, gum softness, visual consistency, and flavor. Any package that fails inspection is flagged, and the rest of its batch is reviewed. All quality records are logged digitally, tying back to the original gum base formulation and mixing parameters. This robust traceability ensures that, in the rare event of a defect or recall, every package's full production history is instantly accessible. Once cleared, the products are palletized and prepared for outbound delivery. Some are shipped to retail distributors, others to vending machine companies, export terminals, or wholesalers. Trucks used for transport are checked for cleanliness and proper loading temperatures to ensure the gum isn't exposed to heat or humidity during transit. Stretch-wrapped pallets are loaded according to weight and stability guidelines, scanned out of the factory system, and then dispatched. Even after leaving the facility, each batch of bubblegum remains traceable, monitored, and accountable. This level of post-production oversight is essential to maintaining brand reliability and consumer trust. It ensures that the bubblegum purchased in a corner store, supermarket, or theme park tastes exactly as intended: sweet, chewy, stretchy, and perfectly made. From polymer blending and base formulation to flavor integration, shaping, wrapping, and final logistics, the entire bubblegum production process is a seamless combination of food science, mechanical precision, and quality management. It's a surprisingly complex journey for a product designed to be fun and carefree, proof that even the most playful confections are supported by a foundation of serious, sophisticated industrial engineering. Hershey's chocolate bars begin their journey long before they ever reach a factory. It all starts with the cocoa bean, the essential ingredient that gives chocolate its signature taste. Cocoa trees grow in the tropical regions of West Africa, South America, and Southeast Asia, where warm temperatures and high humidity create the perfect environment for cacao cultivation. Farmers carefully harvest ripe cocoa pods, slicing them open to extract the cocoa beans nestled inside. These beans are then piled into large heaps or wooden boxes, where they undergo fermentation, a crucial process that develops the deep, complex chocolate flavors. Over several days, the beans are stirred occasionally, allowing natural yeasts and bacteria to work their magic. The result is a transformation from bitter, raw cocoa to something much closer to the chocolate taste that will eventually be refined and perfected in Hershey's factories. Once fermentation is complete, the cocoa beans are spread out under the sun to dry. Farmers rake them periodically to ensure even drying, preventing mold growth and preserving the beans' quality. This drying process can take up to a week, depending on weather conditions. When fully dried, the beans are packed into burlap sacks and shipped across the world to Hershey's chocolate production facilities. The journey from farm to factory is carefully monitored, as the quality of the beans at this stage will significantly influence the final product's taste and texture. Upon arrival at the Hershey factory, the cocoa beans go through a strict quality control process. They are first inspected for size, color, and overall condition. Any beans that do not meet the company's rigorous standards are removed from the batch. Next, the beans are thoroughly cleaned to remove any dust, dirt, or foreign matter that may have accumulated during transport. High-powered air jets and mechanical sifters separate unwanted debris, ensuring that only pure cocoa beans proceed to the next stage. Once cleaned, the cocoa beans move into the roasting phase. Roasting is one of the most important steps in chocolate production, as it intensifies the flavor and brings out the rich, aromatic notes associated with Hershey's signature taste. The beans are poured into large rotating drum roasters, where they are exposed to controlled heat for a specific duration. The precise temperature and roasting time are carefully calibrated based on the desired flavor profile. As the beans roast, their moisture content decreases, and chemical changes occur within the beans, developing the characteristic chocolatey taste. The air inside the roasters is constantly circulated to ensure even roasting, and sensors monitor the temperature to maintain consistency. Once the beans have been roasted to perfection, they are transferred to the winnowing machines. Here, the beans are cracked open, breaking them into smaller fragments called nibs. The outer shells, which are no longer needed, are blown away using air currents, leaving only the rich, flavorful cocoa nibs behind. These nibs contain the essence of chocolate, and they will soon be transformed into a smooth, creamy liquid that serves as the foundation for Hershey's chocolate bars. Meanwhile, another critical ingredient in Hershey's chocolate is being prepared: milk. One of the distinguishing features of Hershey's chocolate is its unique milk treatment process, which contributes to its recognizable flavor. Fresh milk is sourced from dairy farms located near the Hershey factory to ensure freshness. Upon arrival, the milk undergoes pasteurization, a heating process that eliminates harmful bacteria while preserving its nutritional qualities. The milk is then condensed and mixed with sugar, creating a rich, sweetened milk base that will later be combined with the cocoa ingredients. As the cocoa nibs continue their transformation, they are sent to grinding machines, where they are crushed into a thick, liquid paste known as chocolate liquor. Despite the name, chocolate liquor contains no alcohol. It is simply the finely ground form of cocoa solids suspended in cocoa butter. The grinding process generates heat, which helps break down the cocoa particles even further, creating a smooth consistency. The quality of this chocolate liquor is crucial, as it will determine the texture and taste of the final chocolate product. Once the chocolate liquor is ready, it is blended with the sweetened condensed milk mixture, along with additional cocoa butter and sugar. These ingredients come together in large industrial mixers, where they are thoroughly blended to create a uniform chocolate mixture. The goal at this stage is to ensure even distribution of flavors, so the chocolate undergoes multiple rounds of mixing and refining. The refining process is carried out using heavy steel rollers, which reduce the particle size of the chocolate to an ultra-fine consistency. This step is essential for achieving the smooth texture that Hershey's chocolate bars are known for. After refining, the chocolate mixture moves into the conching phase, a process named after the shell-like shape of the original conching machines. Conching involves continuously churning and aerating the chocolate for several hours, helping to develop a silky texture and deepening the flavor. The friction generated by the conching machines warms the chocolate slightly, allowing undesirable acidity and bitterness to dissipate while enhancing the overall creaminess. Hershey's carefully controls the conching process to achieve a balance of flavors that has remained consistent for over a century. Once conching is complete, the chocolate is not yet ready to be molded into bars. It must first undergo tempering. Tempering is a delicate process that involves heating and cooling the chocolate in a precise manner to stabilize the cocoa butter crystals. If chocolate is not properly tempered, it can develop a dull appearance, a grainy texture, or white streaks known as bloom. To prevent this, Hershey's employs advanced tempering machines that carefully regulate the temperature changes, ensuring that the chocolate maintains a glossy finish and a firm, satisfying snap when broken. With the chocolate now perfectly tempered, it is ready to be molded into the iconic Hershey's chocolate bar shape. Liquid chocolate flows into custom-designed molds that feature the signature rectangular segments, each embossed with the Hershey's logo. These molds travel along a conveyor belt through a cooling tunnel, where the chocolate gradually solidifies. The cooling process is precisely controlled to ensure even crystallization, which contributes to the final bar's smooth texture and structure. Once the chocolate has fully set, the bars are carefully removed from the molds and inspected for any imperfections. While the chocolate bars are being formed, the packaging materials are also being prepared. Hershey's chocolate bars are wrapped in a combination of foil and paper, a packaging style that has remained largely unchanged for decades. The foil wrapping helps protect the chocolate from moisture and light, preserving its freshness and preventing it from developing off flavors. The outer paper wrapper, printed with the familiar Hershey's branding, serves as both an aesthetic and informational component, providing details about the product while reinforcing the brand's legacy. As the tempered chocolate flows through the production line, it is maintained at an exact temperature to prevent premature setting. Hershey's factories employ state-of-the-art computerized systems that regulate every aspect of the chocolate's movement, ensuring that the liquid chocolate maintains the ideal viscosity. If the chocolate is too thick, it may not fill the molds evenly. If it is too thin, it may not develop the proper texture once solidified. To maintain this delicate balance, specialized flow control pumps continuously circulate the chocolate through insulated pipes that keep it warm and fluid until the exact moment it is deposited into the molds. The molds themselves are engineered with extreme precision to create the uniform shape and smooth surface that Hershey's chocolate bars are known for. Each mold is made from food-grade polycarbonate material, designed to withstand repeated use while maintaining an ultra-smooth interior that ensures the chocolate releases cleanly once set. These molds travel along a high-speed conveyor belt system, positioned beneath nozzles that dispense the precise amount of liquid chocolate needed to form each bar. Advanced sensors monitor the filling process, making real-time adjustments to ensure that every mold receives an identical amount of chocolate. Once the molds are filled, the next critical step in the process is vibration. The conveyor belt moves the freshly filled molds to a specialized vibrating platform, which gently shakes them at a controlled frequency. This step serves two important purposes. First, it helps remove any trapped air bubbles that could create holes or uneven textures in the final product. Second, it ensures that the chocolate settles evenly within the mold, creating a smooth and uniform appearance. Even the slightest inconsistency in this stage could lead to defects in the bars, so Hershey's quality control team continuously monitors the process to maintain consistency. After vibration, the molds enter a cooling tunnel, a long temperature-controlled chamber that gradually reduces the chocolate's temperature to encourage proper crystallization. This step is crucial for achieving the perfect texture and preventing unwanted fat bloom, which can occur when cocoa butter crystallizes improperly, resulting in a white, powdery appearance on the surface of the chocolate. The cooling tunnel is divided into multiple temperature zones, allowing the chocolate to solidify gradually rather than cooling too quickly, which could cause structural weaknesses or affect the snap of the final bar. As the chocolate sets, it undergoes another round of automated inspection to detect any irregularities. High-resolution cameras and laser scanners analyze each mold, checking for inconsistencies in shape, texture, or surface quality. Any bars that do not meet Hershey's exacting standards are rejected and sent back for remelting, ensuring that no chocolate goes to waste. Once the bars pass inspection, they are gently removed from the molds using an automated demolding system. A combination of slight flexing and compressed air helps separate the bars from the molds without damaging their delicate structure. Now that the chocolate bars have taken their final shape, they must be prepared for packaging. Hershey's packaging process is one of the most sophisticated in the confectionery industry, designed to ensure that each bar remains fresh and protected from environmental factors such as moisture, temperature fluctuations, and physical damage. The first step in packaging involves a high-speed wrapping machine that envelopes each bar in a layer of aluminum foil. This foil serves as a crucial barrier against light and oxygen, both of which can negatively impact the flavor and quality of the chocolate over time. Once the bars are wrapped in foil, they move to the next stage, where the outer paper wrapper is applied. Hershey's iconic packaging, with its bold brown and white branding, is instantly recognizable and has remained largely unchanged for decades. The wrapping machine applies a thin bead of adhesive to secure the paper wrapper in place, ensuring that it remains tightly sealed around the foil-covered chocolate bar. Automated sensors check each wrapped bar for proper alignment, rejecting any that do not meet the strict packaging criteria. With individual bars now fully wrapped, the next step is bundling them into larger packs. Depending on the intended retail format, Hershey's chocolate bars may be packaged as single units, multi-packs, or larger bulk boxes for wholesale distribution. Robotic arms carefully arrange the wrapped bars into predetermined configurations, stacking them into cardboard trays or shrink-wrapped bundles. For multi-packs, additional layers of protective film are applied to keep the bars securely together, preventing shifting during transportation. As the packaged chocolate bars move down the production line, they are assigned a unique batch code and expiration date, which are printed onto each wrapper using high-speed inkjet printers. This information is essential for inventory tracking, ensuring that products are rotated properly in warehouses and retail stores. It also allows Hershey's quality control team to trace any potential issues back to a specific production batch if necessary. Once all packaging steps are complete, the finished Hershey's chocolate bars are sent through final inspection before being prepared for shipment. Automated weight sensors check each package to ensure that no product is missing or underweight. Any deviations from the standard weight result in the package being removed from the line for manual inspection. After passing this final quality check, the bars are packed into large shipping cartons, which are sealed and labeled for distribution. The shipping process is a carefully orchestrated operation designed to maintain the integrity of the chocolate during transit. Hershey's distribution centers are equipped with climate-controlled storage areas, ensuring that chocolate is kept at an optimal temperature before being shipped to retailers worldwide. The pallets of chocolate bars are loaded onto refrigerated trucks, which maintain a consistent temperature to prevent melting or fat bloom. During summer months or in regions with particularly hot climates, additional measures are taken, such as using insulated packaging to further protect the chocolate from heat exposure. From the distribution centers, Hershey's chocolate bars are shipped to grocery stores, convenience stores, vending machines, and online retailers. The entire process, from sourcing cocoa beans to the moment a consumer unwraps a bar, is the result of years of expertise, precise engineering, and a deep commitment to quality. Hershey's has spent over a century refining its production methods, leveraging cutting-edge technology while preserving the craftsmanship that has made its chocolate a household favorite. Even after reaching store shelves, Hershey's continues to monitor product freshness through a network of distributors and retail partners. Inventory rotation practices ensure that consumers always receive the freshest possible product, with older stock being sold before newer shipments are placed on shelves. The brand's commitment to quality extends beyond just manufacturing. It includes every aspect of the supply chain, from sourcing raw ingredients to delivering the final product into the hands of consumers. As the packaged chocolate bars leave the production line, they move through an automated sorting system that directs them to the correct pallets for shipment. Robotic arms, programmed with artificial intelligence and real-time scanning capabilities, ensure that each batch is assigned to the right destination. Whether the chocolate bars are heading to domestic supermarkets, international retailers, or specialized distributors, each shipment is meticulously tracked using barcode scanning and digital inventory management systems. Hershey's has invested heavily in supply chain optimization, integrating real-time data analytics to monitor product flow, track expiration dates, and prevent overstocking or shortages. The process of transporting chocolate requires specific environmental controls. Hershey's distribution centers are equipped with temperature-controlled storage facilities to prevent the chocolate from being exposed to excessive heat or humidity. If chocolate bars are stored in less than ideal conditions, the risk of bloom increases. Fat bloom, the most common issue, occurs when the cocoa butter in the chocolate migrates to the surface, creating a dull, whitish coating. Sugar bloom, on the other hand, happens when moisture causes sugar crystals to form on the surface of the chocolate, resulting in a rough texture. While neither of these phenomena makes the chocolate unsafe to eat, they can negatively impact consumer perception and overall product quality. To prevent these issues, Hershey's carefully maintained storage temperatures between 65 degrees Fahrenheit and 70 degrees Fahrenheit, ensuring that the chocolate remains in optimal condition before it reaches retailers. Once the chocolate bars are loaded onto trucks, their journey continues. Hershey's logistics team coordinates shipments using a combination of ground transportation, air freight, and sea freight, depending on the destination. Domestic shipments typically travel via temperature-controlled trucks, while international shipments require specialized shipping containers equipped with insulation and climate control technology. Each step of transportation is monitored to ensure that the chocolate remains in a stable environment, preventing any degradation in quality. At retail distribution centers, Hershey's chocolate bars are unloaded and sorted based on regional demand. Large grocery chains and supermarkets often have automated warehouse systems that use conveyor belts and robotic picking technology to distribute inventory efficiently. Hershey's works closely with retailers to ensure that the product is stocked properly, preventing situations where chocolate sits in storage too long before being placed on shelves. This level of coordination ensures that customers receive the freshest possible product. Inside stores, Hershey's chocolate bars are positioned strategically to maximize sales. The company's marketing and sales teams work with retailers to determine optimal placement, typically near checkout aisles, in candy sections, and in promotional display stands designed to attract impulse buyers. Hershey's has spent years researching consumer behavior, using data-driven insights to refine its approach to in-store merchandising. Seasonal variations, such as Halloween, Christmas, and Valentine's Day bring about limited edition packaging and themed chocolate products that are prominently displayed to boost sales during peak shopping periods. While the chocolate bars are now readily available for purchase, Hershey's commitment to quality control does not stop at the point of sale. The company maintains a rigorous consumer feedback system, allowing customers to report any quality concerns or irregularities. If a batch of chocolate bars is found to have any defects, Hershey's can trace the issue back to a specific production lot using the batch codes printed on each wrapper. This traceability ensures that any necessary corrective actions, such as recalls or reformulation, can be implemented quickly and efficiently. Hershey's also invests heavily in food safety measures, adhering to strict regulatory standards set by organizations such as the US Food and Drug Administration, FDA, the Food Safety Modernization Act, FSMA, and Global Food Safety Initiatives. In addition to routine quality checks throughout production, the company conducts random sampling of finished chocolate bars to test for microbial contamination, ingredient consistency, and adherence to allergen labeling guidelines. Every aspect of production, from ingredient sourcing to final packaging, is governed by good manufacturing practices, GMP, to ensure consumer safety. Beyond the standard Hershey's milk chocolate bar, the company's factories are also responsible for producing a variety of chocolate products that follow similar manufacturing principles, but may involve additional steps. For example, Hershey's with almonds requires an extra stage where roasted almonds are added to the chocolate mixture before molding. Similarly, cookies and cream variations include white chocolate blended with crunchy cocoa cookie pieces, requiring specialized mixing equipment to distribute the inclusions evenly throughout the bar. These variations highlight the flexibility of Hershey's production facilities, which are designed to accommodate multiple product lines while maintaining consistent quality. Sustainability has become an increasing focus for Hershey's in recent years. The company has taken significant steps toward reducing its environmental impact, particularly in cocoa sourcing and packaging waste reduction. Through its Cocoa for Good initiative, Hershey's invests in sustainable cocoa farming practices, providing training and financial support to farmers in West Africa and Latin America. These efforts not only help improve cocoa yields, but also ensure ethical labor practices and environmental conservation. Additionally, Hershey's has committed to using more recyclable packaging materials, reducing plastic waste in its supply chain, and lowering its carbon footprint through energy-efficient manufacturing practices. Innovation continues to drive the future of Hershey's chocolate bars. The company's research and development teams are constantly exploring new formulations, textures, and flavors to keep up with changing consumer preferences. Whether it's introducing sugar-free or plant-based chocolate alternatives, experimenting with new ingredients, or enhancing the nutritional profile of its products, Hershey's remains at the forefront of confectionery innovation. The brand has also embraced digital marketing and e-commerce, expanding its presence in online grocery platforms, direct-to-consumer sales, and subscription-based chocolate delivery services. Despite all the advancements in production technology and distribution, the core experience of enjoying a Hershey's chocolate bar remains unchanged. The familiar taste, creamy texture, and satisfying snap of the chocolate have made it a beloved treat for generations. Each bar carries with it the legacy of Milton Hershey's original vision, a high-quality chocolate product that is both accessible and affordable to consumers around the world. Looking ahead, Hershey's will continue to evolve, adapting to new market demands while staying true to the craftsmanship and quality that have defined the brand for over a century. As technology progresses, automation and artificial intelligence will play an even greater role in optimizing production efficiency, ensuring that every Hershey's chocolate bar maintains the same level of consistency and excellence. The commitment to quality, sustainability, and innovation will continue to shape the future of Hershey's chocolate, ensuring that it remains a staple in households for generations to come. The Hershey's chocolate bar, a product that has been enjoyed for over a century, is the result of a complex and highly controlled manufacturing process that blends tradition with cutting-edge technology. While the chocolate has already gone through its journey from raw cocoa beans to finished bars, wrapped and ready for sale, the process does not end there. The company continues to ensure product integrity even after distribution, keeping an eye on market trends, customer satisfaction, and ongoing improvements in production methods. Once the chocolate bars reach stores, Hershey's relies on a vast retail network to keep the product readily available for consumers. Supermarkets, convenience stores, vending machines, and online retailers all play a role in ensuring that Hershey's chocolate bars are accessible in virtually every corner of the market. In addition to traditional sales channels, Hershey's has expanded into direct-to-consumer models, offering limited edition flavors and exclusive packaging through its website and specialty stores. This move allows consumers to order their favorite Hershey's products from the comfort of their homes, ensuring freshness and convenience. Marketing plays a crucial role in maintaining Hershey's dominance in the chocolate industry. The brand has built an emotional connection with consumers, often associating its chocolate bars with childhood nostalgia, holidays, and shared moments. Advertising campaigns, social media promotions, and in-store displays reinforce the brand's image, keeping it relevant across generations. Hershey's also engages in sponsorships and collaborations, partnering with other food companies to create innovative products such as Hershey's infused baked goods, cereals, and ice cream flavors. Quality control remains a top priority even after the bars leave the factory. Hershey's has consumer feedback channels where customers can report any issues, such as damaged packaging or quality inconsistencies. The company takes such feedback seriously, using it to refine manufacturing processes and enhance overall product quality. If a defect is traced back to a specific batch, Hershey's can quickly analyze production data to determine the cause and prevent future occurrences. This level of traceability is made possible by sophisticated tracking systems that log every step of the manufacturing and distribution process. Sustainability continues to be an integral part of Hershey's long-term vision. The company is committed to ethical cocoa sourcing, reducing carbon emissions, and minimizing waste in its production facilities. Efforts include switching to more eco-friendly packaging materials, optimizing energy use in factories, and investing in cocoa farming communities to improve agricultural sustainability. By implementing these initiatives, Hershey's aims to balance business growth with environmental responsibility, ensuring that future generations can continue to enjoy its chocolate without negatively impacting the planet. Innovation is also a driving force behind Hershey's success. The company constantly experiments with new flavors, textures, and formulations, responding to emerging consumer trends such as sugar-free, high-protein, and plant-based alternatives. Research and development teams work on improving not only the taste, but also the nutritional profile of chocolate, making it more appealing to health-conscious consumers. Additionally, Hershey's has explored advancements in manufacturing efficiency, incorporating AI-driven quality checks, automation in packaging, and precision temperature control systems to maintain the highest standards in chocolate production. Despite all these advancements, the core experience of enjoying a Hershey's chocolate bar remains timeless. The simple act of unwrapping a bar, breaking off a square, and savoring the smooth, creamy texture is a universal pleasure that spans generations. Hershey's success lies in its ability to evolve while staying true to its heritage, ensuring that the chocolate remains as beloved today as it was when Milton Hershey first introduced it. Looking forward, Hershey's will continue to adapt to changing market dynamics while upholding the traditions that have defined its chocolate for over a century. Whether through expanding into new markets, refining sustainability practices, or leveraging technological innovations, the brand remains committed to delivering the same high-quality chocolate experience that consumers know and love. From the cocoa farms where it all begins to the final moment when a Hershey's chocolate bar is enjoyed, every step in the process is a testament to dedication, precision, and the enduring appeal of one of the world's most iconic chocolate brands. Producing the world's most beloved chocolate bars isn't just about great ingredients, it's a precision-driven process on an unbelievable scale. Every day, millions of Cadbury dairy milk bars are crafted inside state-of-the-art factories, where advanced machinery and carefully refined techniques transform raw cocoa into the smooth, creamy chocolate people love. The creation of a Cadbury dairy milk bar begins long before the chocolate reaches the factory. It starts on cacao farms located in tropical regions near the equator, where the conditions are ideal for growing cacao trees. The trees require warm temperatures, high humidity, and consistent rainfall to produce the cacao pods that contain the beans essential for making chocolate. These pods grow directly from the branches and trunk of the tree, taking around 6 months to mature. Farmers carefully monitor the pods, waiting until they turn from green to yellow, orange, or deep red, indicating ripeness. Harvesting is a meticulous process, as improper handling can damage the delicate cacao tree. Skilled workers use sharp machetes to cut the ripe pods from the tree, ensuring that the branch is left intact so that future pods can develop. Once harvested, the cacao pods must be processed immediately to prevent spoilage. The first step involves cracking open the thick, leathery shells to reveal the beans inside, which are surrounded by a sweet, sticky pulp. Farmers often use wooden clubs or knives to split the pods, being careful not to damage the beans within. Each pod contains around 30 to 50 beans, and thousands of these are needed to produce a single chocolate bar. The extracted beans and pulp are then placed into large wooden fermentation boxes, which are arranged in stacks to allow for air circulation. Fermentation is a crucial step in the chocolate making process, as it develops the complex flavors that will later be enhanced during roasting. The beans are left to ferment for 5 to 8 days, during which time they undergo chemical changes that transform their taste. The natural yeasts in the pulp break down the sugars, generating heat and causing the temperature inside the fermentation boxes to rise. This heat triggers biochemical reactions within the beans, breaking down their natural bitterness and releasing the precursor compounds that will later give chocolate its distinctive aroma and flavor. To ensure even fermentation, workers turn the beans periodically, usually once a day. This helps to distribute heat and oxygen throughout the pile while allowing excess moisture to evaporate. During this time, the beans gradually darken in color and develop a rich, earthy aroma. Without proper fermentation, the beans would retain a raw, astringent taste, resulting in low-quality chocolate. After fermentation is complete, the beans must be dried to reduce their moisture content and prepare them for transport. Traditionally, drying is done by spreading the beans out on large wooden trays or concrete surfaces under the sun. The drying process can take anywhere from 5 to 7 days, depending on the weather conditions. Workers frequently rake the beans to ensure they dry evenly and prevent mold growth. If the climate is too humid or rainy, mechanical dryers may be used to speed up the process and maintain quality standards. Once fully dried, the cacao beans are carefully sorted to remove any defective or damaged ones before being packed into jute sacks for shipment. These sacks are transported from cacao-producing countries to chocolate manufacturing facilities worldwide, including those used by Cadbury. Upon arrival at the factory, the first step in the production process is cleaning. The beans are loaded onto conveyor belts and passed through a series of cleaning machines that remove dirt, dust, and any remaining plant material. This ensures that only the highest quality beans proceed to the next stage. After cleaning, the beans are roasted to further develop their flavor. The roasting process is highly controlled, with temperatures and durations carefully calibrated to achieve the desired taste profile. The exact roasting conditions vary depending on the type of chocolate being produced, but for Cadbury Dairy Milk, the beans are typically roasted at temperatures between 120 to 150 degrees Celsius for about 30 to 45 minutes. During roasting, the beans undergo the Maillard reaction, a chemical process that enhances their flavor and aroma by breaking down proteins and sugars. The heat also causes the thin outer shells of the beans to become brittle, making them easier to remove in the next step. Once roasting is complete, the beans are cooled and sent through a machine called a winnower. This machine cracks the beans open, separating the outer shells from the inner nibs. The shells are removed using powerful air jets, leaving behind the pure cacao nibs, which contain the essential cocoa solids and cocoa butter needed for chocolate production. The nibs are then ground into a thick, liquid paste known as cocoa mass or cocoa liquor. This process is done using industrial grinding machines that apply high pressure to break down the nibs into tiny particles. The resulting cocoa mass has a rich, intense chocolate flavor, but is still quite coarse in texture. At this stage, the cocoa mass can be further processed to extract cocoa butter, a key ingredient in chocolate making. The mass is placed into hydraulic presses, which apply immense pressure to separate the fat, cocoa butter, from the solid components, cocoa solids. The extracted cocoa butter is a pale yellow, creamy substance that gives chocolate its smooth and creamy mouthfeel. Meanwhile, the remaining cocoa solids are ground into a fine powder, which can be used for making cocoa powder or reintroduced into the chocolate mixture for added richness. For Cadbury Dairy Milk, the next crucial step is blending the cocoa mass with other key ingredients, sugar and milk powder. Unlike dark chocolate, which relies on cocoa solids as the primary component, dairy milk chocolate has a significant proportion of milk, giving it a distinctively creamy texture and flavor. Cadbury uses fresh milk in its production process rather than relying solely on milk powder, a method that differentiates its chocolate from many other brands. The fresh milk is collected from dairy farms and transported in refrigerated tankers to the factory, where it undergoes quality control checks to ensure purity and freshness. Upon arrival, the milk is pasteurized to eliminate harmful bacteria and then concentrated to reduce its water content. This is achieved through a process called vacuum evaporation, in which the milk is heated under reduced pressure to remove excess moisture while preserving its natural flavor. The concentrated milk is then mixed with sugar to form a sweetened milk mixture, which is later blended with the cocoa mass. This unique approach, known as the creme process, involves heating the milk and sugar together before adding them to the chocolate mixture. This technique enhances the caramelized notes of the chocolate and contributes to Cadbury's signature flavor. Once the cocoa mass, milk, and sugar are combined, the mixture undergoes refining to achieve a smooth consistency. Industrial refining machines use heavy rollers to grind the chocolate mixture, reducing the particle size to an ultra-fine level. This step is essential for creating the smooth, velvety texture that defines Cadbury Dairy Milk. If the particles are too large, the chocolate will have a grainy, rough mouthfeel, so precision in refining is crucial. The refined chocolate mixture, now resembling a dry, powdery substance, is ready for the next stage, conching. Conching is a continuous mixing and aeration process that further develops the chocolate's flavor and texture. The mixture is placed into large conching machines, where it is continuously stirred and heated for several hours. The duration of conching varies depending on the desired final texture and flavor, but for Cadbury Dairy Milk, it typically lasts between 4 to 6 hours. During this process, the chocolate's acidity and bitterness are reduced, while the smoothness and richness are enhanced. The heat and friction generated during conching also help to distribute the cocoa butter evenly, ensuring that the chocolate has a uniform texture. Once the conching process has refined the chocolate mixture into a smooth and well-developed liquid, it must undergo a crucial process known as tempering. Tempering is an essential step in chocolate production that ensures the final chocolate bars have a glossy finish, a firm structure, and the characteristic snap when broken. This process involves carefully controlling the temperature of the chocolate to stabilize the cocoa butter crystals. Cocoa butter exists in multiple crystalline forms, but only one of them, the beta crystal structure, provides the ideal texture and appearance for chocolate bars. If the chocolate is not tempered correctly, it can develop an unattractive, dull, or streaky surface and a grainy texture. Tempering is achieved through a series of precise temperature adjustments. First, the liquid chocolate is gradually cooled to around 27 to 28 degrees Celsius, which encourages the formation of stable beta crystals. Then, the temperature is raised slightly to about 31 to 32 degrees Celsius for milk chocolate, melting any unwanted crystal structures while keeping the stable ones intact. This ensures that when the chocolate cools and solidifies in the molds, it will have a smooth and uniform consistency. Large-scale chocolate tempering machines, which are fully automated, are used in Cadbury's factories to maintain this process with extreme precision. These machines continuously agitate the chocolate while controlling its temperature at various stages, ensuring that the cocoa butter crystallizes correctly. Once tempering is complete, the chocolate is ready for molding. The tempered chocolate is transferred to an automated molding system where it is poured into specially designed molds that give Cadbury dairy milk bars their iconic shape and thickness. The molds are made of food-grade polycarbonate plastic or stainless steel and are designed to create perfectly uniform chocolate bars. The molding system ensures that each bar receives the precise amount of liquid chocolate needed for consistent weight and shape. To ensure that the chocolate fills every crevice of the mold and eliminates any trapped air bubbles, the molds pass through a vibrating station. This high-frequency vibration gently shakes the molds, allowing the liquid chocolate to settle evenly and remove any unwanted air pockets. This step is crucial in creating a uniform texture throughout the bar, as any trapped air can lead to weak spots or inconsistencies in the final product. Once the chocolate is evenly distributed in the molds, the bars must be cooled to solidify completely. The molds move along a conveyor belt into a cooling tunnel, a temperature-controlled environment that gradually reduces the temperature of the chocolate. Cooling must be done gradually to prevent the formation of sugar or fat bloom, which can create a white or grayish appearance on the surface of the chocolate. The cooling tunnels are typically set at temperatures between 5 to 10 degrees Celsius, and the bars spend around 20-30 minutes inside, depending on their thickness and size. During this time, the chocolate transitions from a liquid state to a solid form with a firm structure and smooth texture. After cooling, the solidified chocolate bars are carefully removed from the molds using an automated demolding system. This process is designed to be gentle to prevent breakage, ensuring that each bar maintains its perfect shape. The bars are then sent along conveyor belts for the next stage, quality inspection. At this point, every chocolate bar undergoes a thorough quality control check to ensure it meets Cadbury's strict standards. High-speed cameras and laser sensors scan the chocolate bars for any imperfections, such as cracks, air bubbles, or irregular shapes. Bars that do not meet quality standards are removed from the production line and either reprocessed or discarded. Factory workers also conduct random manual inspections, checking for surface smoothness, uniform thickness, and the signature Cadbury dairy milk texture. Once the bars have passed the quality inspection stage, they move on to the packaging process. Packaging is an essential part of chocolate production, as it protects the chocolate from external factors such as moisture, air, and temperature changes that could affect its quality. The packaging process begins with automated machines wrapping each chocolate bar in a protective layer. Traditionally, Cadbury dairy milk bars were wrapped in foil with a paper sleeve, but modern packaging now consists of a specially designed plastic film that provides better sealing and protection. The packaging machines work at incredibly high speeds, wrapping hundreds of chocolate bars per minute. Each bar is precisely aligned and fed into the packaging machine, where the plastic film is cut and wrapped tightly around it. Heat sealing technology ensures that the package is securely sealed, keeping the chocolate fresh and protected from environmental factors. Once wrapped, the bars are sent through a labeling station, where product information such as batch numbers, expiration dates, and barcodes are printed onto the packaging. After labeling, the individually wrapped chocolate bars are grouped together into larger multi-packs or cartons, depending on the intended retail format. These multi-packs are then placed into shipping boxes, which are sealed and prepared for distribution. To ensure efficiency in the supply chain, Cadbury's factory uses automated robotic systems to stack the finished boxes onto pallets. These robotic arms work with incredible precision, organizing the boxes in a way that maximizes space while ensuring stability during transport. The pallets of Cadbury Dairy Milk bars are then transferred to the factory's storage and distribution center, where they are kept in temperature-controlled warehouses before being shipped to retailers worldwide. The storage conditions are carefully maintained to prevent temperature fluctuations, as chocolate is highly sensitive to heat and humidity. Ideal storage temperatures for chocolate typically range between 15 to 18 degrees Celsius to prevent melting, fat bloom, or sugar crystallization. Once ready for distribution, the chocolate bars are loaded onto refrigerated trucks and transported to supermarkets, convenience stores, and other retail outlets. Cadbury ensures that strict logistics and transportation protocols are followed to maintain the quality of the chocolate during transit. These trucks are equipped with temperature-controlled systems that prevent overheating or exposure to extreme temperatures, ensuring that the chocolate arrives in perfect condition. Upon arrival at retail locations, the chocolate bars are displayed on store shelves, ready for consumers to purchase. The iconic purple packaging and recognizable branding make Cadbury Dairy Milk one of the most easily identifiable chocolate products on the market. From the initial stages of cacao cultivation to the moment a customer unwraps a bar, every step in the production process is meticulously designed to deliver the perfect balance of smoothness, creaminess, and rich chocolate flavor that has made Cadbury Dairy Milk a favorite for generations. The next stage in the manufacturing process is focused on large-scale efficiency, ensuring that every single Cadbury Dairy Milk bar produced maintains the same level of quality, texture, and taste. Once the bars are molded, cooled, and packaged, the production line moves seamlessly into the next critical phase: quality control and inspection. While some initial checks were already performed during molding and packaging, this stage is dedicated to an in-depth analysis of every batch to guarantee consistency. Cadbury employs an extensive quality control system using a combination of automated technology and human oversight. High-speed cameras and infrared scanners are positioned along the conveyor belts to detect any visible imperfections, such as cracks, surface defects, or uneven molding. These sophisticated imaging systems compare each chocolate bar against a pre-programmed reference model, instantly flagging any inconsistencies. Defective bars are automatically removed from the production line and sent to a separate area where they may be either reprocessed or discarded depending on the severity of the defect. Beyond the physical appearance of the bars, texture and taste are also key factors that must be evaluated. Every production batch undergoes sample testing, where factory workers manually inspect a random selection of bars, breaking them to listen for the characteristic snap that signifies proper tempering. The texture is also analyzed using precision measuring instruments that evaluate the chocolate's density and uniformity. To maintain Cadbury's signature creamy mouthfeel, particle size analysis is conducted to ensure that the chocolate's refined mixture maintains a smooth consistency. If any deviations are detected, the production settings are adjusted in real time to correct potential issues before they impact the entire batch. In addition to visual and textural inspections, extensive taste testing is performed. Cadbury employs trained sensory panels, experts with highly developed palates, to sample and evaluate each batch of dairy milk chocolate. These professionals assess the chocolate for its signature balance of sweetness, creaminess, and cocoa richness. The sensory panelists follow a structured evaluation process, examining attributes such as melt rate, lingering aftertaste, and flavor complexity. To ensure objective results, the tasters follow strict guidelines, such as cleansing their palates between samples and tasting in a controlled environment, free from external odors or distractions. Once the quality control stage is successfully completed, the chocolate bars proceed to the final stage of distribution. At this point, thousands of bars are packed into cartons and prepared for shipment. The logistics of distributing Cadbury Dairy Milk bars to retailers worldwide is a highly coordinated effort. Each carton is scanned, labeled, and sorted based on its destination. Advanced inventory management systems track every unit in real time, ensuring that supply chain operations remain smooth and efficient. Temperature-controlled storage is an essential part of this process. Since chocolate is highly sensitive to temperature and humidity, Cadbury warehouses maintain precise environmental conditions. Storage temperatures are carefully kept within the optimal range of 15 to 18 degrees Celsius to prevent issues such as fat bloom, a white discoloration caused by fat migration, or sugar bloom, a grainy surface texture caused by moisture exposure. To further protect the chocolate, humidity levels in the warehouse are monitored to prevent condensation from forming inside the packaging. Once the chocolate bars are ready for transport, they are loaded onto specially designed delivery trucks equipped with temperature regulation systems. These vehicles are programmed to maintain ideal conditions throughout transit, ensuring that the chocolate does not melt or suffer quality degradation. The bars are then transported to distribution centers, where they are sorted and prepared for delivery to supermarkets, convenience stores, and online retailers. The final stage of the Cadbury Dairy Milk Bar's journey, from its creation in the factory to reaching the hands of consumers, is a combination of advanced logistics, careful storage, and precise distribution. Ensuring that millions of chocolate bars arrive in perfect condition across the globe requires an intricate supply chain. Every Cadbury Dairy Milk bar, once fully manufactured, undergoes a detailed process of warehousing, transportation, retail placement, and eventual purchase by consumers. After passing rigorous quality control checks, the packaged chocolate bars are sent to Cadbury's automated warehousing facilities. These warehouses are designed with climate control systems that maintain optimal conditions for chocolate storage. Chocolate is highly sensitive to temperature fluctuations and humidity, which can lead to fat bloom or sugar bloom if not stored correctly. Fat bloom appears as a whitish discoloration on the chocolate surface, caused by unstable cocoa butter rising to the surface when exposed to inconsistent temperatures. Sugar bloom, on the other hand, results from moisture interacting with sugar particles, causing a rough and grainy texture. To prevent these defects, Cadbury's warehouses maintain a consistent temperature range of 15 to 18 degrees Celsius and humidity levels below 50%. Within the warehouse, an automated storage and retrieval system organizes and categorizes the chocolate bars based on their batch numbers and expiration dates. These systems use robotic arms and conveyor systems to efficiently stack and move cartons of dairy milk bars without human intervention, ensuring minimal handling and reducing the risk of damage. Advanced barcode and RFID scanning technology is employed to track every individual batch, allowing real-time monitoring of inventory levels. This ensures that products are shipped in the correct order, prioritizing freshness and reducing waste. Once ready for distribution, the Cadbury Dairy Milk bars are loaded onto transport trucks for delivery. The logistics of transporting chocolate require carefully planned routes and specially equipped vehicles to prevent exposure to extreme temperatures. In warmer climates, refrigerated trucks are used to maintain the optimal temperature during transport. These trucks are fitted with sensors that continuously monitor temperature conditions, ensuring that any fluctuations can be corrected before they affect the product's quality. From the warehouse, the chocolate bars are delivered to national and international distribution centers. These hubs play a crucial role in breaking down large shipments into smaller deliveries destined for specific retailers. Here, logistics teams coordinate the efficient redistribution of the products to supermarkets, convenience stores, online retailers, and vending machine suppliers. The entire process is optimized using software systems that calculate the most efficient routes and delivery schedules, reducing transit time and ensuring the freshest product reaches store shelves as quickly as possible. Upon arriving at retail locations, Cadbury dairy milk bars are placed in designated areas based on carefully planned merchandising strategies. Retailers follow specific guidelines to position the chocolate bars in high-traffic areas, maximizing visibility and impulse purchases. Supermarkets often stock dairy milk bars in checkout aisles, where customers are more likely to grab a bar as a last-minute addition to their purchases. Convenience stores and gas stations also follow similar placement strategies, ensuring that dairy milk bars are easily accessible and prominently displayed. Beyond traditional retail spaces, online shopping has become an increasingly important channel for Cadbury dairy milk sales. E-commerce platforms allow consumers to order chocolate bars directly from Cadbury or through third-party retailers. These online orders are fulfilled from dedicated warehouses where products are carefully packed to prevent breakage during shipping. Insulated packaging may be used in regions with hot climates to ensure that the chocolate remains solid during transit. Subscription services and bulk purchasing options also contribute to the growing presence of dairy milk in the online marketplace. Once the chocolate bar reaches the hands of the consumer, the experience of enjoying Cadbury dairy milk is the culmination of a long and carefully controlled process. The signature smooth texture and rich taste of the chocolate are as a result of every meticulous step taken throughout the journey, from the cacao farms to the final packaging. The unique flavor of dairy milk is achieved through the combination of high-quality cocoa beans, fresh milk, and precisely controlled manufacturing techniques. In addition to producing high-quality chocolate, Cadbury is also committed to sustainability and ethical sourcing. The company's partnership with the Cocoa Life program ensures that the cocoa used in dairy milk bars is sourced responsibly. This initiative works directly with cocoa farmers to improve farming practices, provide fair wages, and promote environmental conservation. By investing in sustainable cocoa production, Cadbury helps to support the livelihoods of farmers while ensuring a stable and high-quality supply of cocoa for the future. Similarly, Cadbury has made strides in reducing its environmental footprint in manufacturing and packaging. The company is working towards more sustainable packaging solutions, aiming to reduce plastic waste and increase recyclability. Innovations such as thinner plastic film, recyclable paper-based wrappers, and biodegradable packaging materials are being developed to align with global sustainability goals. In the manufacturing process, energy-efficient machinery and waste reduction programs contribute to minimizing the factory's carbon footprint. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold and they won't disperse evenly. Too hot and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small, motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of 2 primary components, a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase, baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from over-processing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts, equipped with vision systems, scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal. The base product of every Cheeto is degermed cornmeal, derived from a variety of field corn that is specially cultivated for its high starch content and low fat levels. This corn must produce a uniform, predictable puff when subjected to extreme heat and pressure, so its density, moisture content, and kernel hardness are closely monitored even at the agricultural stage. Farmers contracted by the manufacturer are required to meet tight tolerances in grain quality, harvesting methods, and post-harvest drying to ensure the raw corn will meet the standards for industrial puffed snack production. Once harvested and transported to the ingredient supplier, the corn undergoes an initial cleaning to remove plant debris, soil, and foreign materials. It is then taken through a degermination process, in which the outer bran layer and the germ, the oil-rich, nutrient-dense part of the corn kernel, are removed. This step is essential. While germ and bran contain healthy fats and proteins, their presence can negatively impact the expansion properties and shelf life of the final product. Germ oil can go rancid over time and interfere with the consistent puff structure that defines a Cheeto. What remains after degermination is the starchy endosperm, milled down into a fine cornmeal that becomes the building block of every puff. This cornmeal is then enriched with a blend of vitamins and minerals, including riboflavin, niacin, iron, and folic acid. The enrichment not only helps meet nutritional labeling requirements, but also contributes to uniformity in the extrusion process, as these additives influence how the mixture reacts under heat and pressure. The resulting product is a dry, golden yellow flour with a specific granulation profile tailored to the plant's extrusion parameters. Before it is used on the production line, the cornmeal is stored in temperature and humidity-controlled silos directly connected to the processing plant. These silos often hold hundreds of metric tons of product and are designed to keep the cornmeal in a stable state for extended periods. Pneumatic systems transfer the cornmeal through stainless steel pipelines to weigh hoppers on the factory floor, where batch sizes are precisely measured. Real-time inventory sensors track the flow of material and communicate with the factory's central control system to automatically replenish supply lines as needed, ensuring uninterrupted production. Now it's time for the first transformation phase, hydration and preconditioning. The cornmeal is metered into a continuous mixing system where it is blended with water or steam to raise its moisture content to a narrowly specified range, usually between 15% and 20%. This step is essential to prepare the starch molecules for gelatinization. The equipment used here is not unlike a ribbon blender or paddle mixer, which agitates the mixture thoroughly to ensure every granule of cornmeal is evenly hydrated. Water is introduced through atomizing nozzles positioned at calculated intervals along the mixer's length, and multiple moisture sensors along the pathway feed back to the PLC system to adjust water input in real time. This moist mixture, often referred to as dough, despite its loose, crumbly texture, is held briefly in a conditioning tank to allow for even moisture distribution. The temperature and residence time are carefully controlled. If the mix is too hot or too wet, it may pre-gelatinize and clog the extruder. Too dry, and it won't expand properly. During this stage, the product is slowly moved along a jacketed screw conveyor that maintains a consistent temperature and prevents clumping. Now we arrive at the heart of the production line, the extruder. Industrial Cheetos are made using a twin screw extruder, one of the most sophisticated and critical machines in the plant. The twin screw configuration allows for highly controlled processing of the corn mixture, providing better mixing, higher shear, and superior control over temperature and pressure compared to single screw models. The hydrated cornmeal is fed into the extruder barrel, where it encounters two rotating screws that convey the material forward under intense mechanical pressure. External heaters line the barrel and raise the temperature incrementally as the product moves through each zone. Inside, shear forces generated by the screws convert some of this mechanical energy into heat, further increasing the temperature of the dough. The intense conditions inside the extruder, pressure in the range of 200 to 500 psi, and temperatures from 130 degrees Celsius to 180 degrees Celsius, cause the starches in the cornmeal to gelatinize and the water to superheat. The dough undergoes plasticization, becoming a molten mass under pressure. As this molten dough reaches the end of the barrel, it is forced through a die, the precision-crafted metal plate that defines the shape of the puff. The die hole is round and small, but as the dough exits into atmospheric pressure, the superheated water in the mixture flashes into steam, causing the structure to puff and expand dramatically in a fraction of a second. This rapid expansion is responsible for the iconic airy texture of a Cheeto. Just outside the die, rotating knives spin at high speed, slicing the continuous stream of puff into uniformly sized segments. The speed of the knives determines the length of the puff, while the pressure and temperature within the extruder affect its diameter and density. But even after this high-tech transformation, the newly extruded Cheetos are far from finished. They are still pale, moist, and bland, essentially unseasoned corn puffs. The next stage is all about turning them into the crunchy, craveable snack that consumers instantly recognize. First, the extruded pieces are conveyed via vibrating trays to a frying system. Here, they're submerged in hot oil, typically corn or canola oil, at carefully controlled temperatures ranging between 160 degrees Celsius and 180 degrees Celsius. The residence time in the fryer is only about 20 to 40 seconds, but in that time, the moisture content is reduced dramatically from around 15% to under 2%. This not only creates the final crispy texture, but also deepens the color slightly, giving the snack its characteristic golden hue. The fryer itself is a marvel of engineering, equipped with multiple sensors and filtration systems. Oil turnover rates are high, meaning that fresh oil is constantly added, while spent oil is removed and filtered to maintain quality. Skimmers remove any floating particles, and oil chemistry is monitored for signs of oxidation, free fatty acid levels, and polymerization. If any readings fall outside of the strict parameters, the fryer automatically triggers corrective actions, dosing with fresh oil, increasing filtration, or even pausing the line to prevent compromised batches from continuing downstream. After exiting the fryer, the Cheetos are carried on mesh conveyors through an air cooling tunnel. High-powered fans blow ambient or conditioned air over the freshly fried snacks, bringing them to a safe handling temperature and ensuring any surface oil solidifies just slightly to help the seasoning adhere. These cooling conveyors are extended and designed with soft vibratory motion to prevent breakage, ensuring that the delicate puffs remain intact before entering the seasoning phase. Next, the Cheetos are transferred into a massive rotating flavor drum, where their bland exterior is transformed by a shower of powdered cheese blend. But before we dive into the complexities of seasoning, we'll need to explore how oil coating is applied for adhesion and how powder distribution systems are calibrated to ensure every single puff gets the perfect amount of flavoring. This next part of the production process is where precision meets sensory science, and the result is the addictively cheesy snack that has become a global favorite. Now it's time to dive into one of the most iconic and intricate stages in Cheetos manufacturing, the flavoring phase. This is where the bland, puffed, and fried corn kernels are transformed into the intensely savory, cheese-coated snacks recognized all over the world. The process of seasoning Cheetos is not merely about tossing on a bit of cheese powder. It is an engineered, tightly controlled operation that determines product consistency, taste balance, visual appeal, and even mouthfeel. Everything from the size and porosity of the puff to the electrostatic charge of the powder particles is taken into account in this phase. After exiting the cooling conveyor from the fryer, the puffs are transferred into large rotating cylindrical drums called flavor tumblers. These drums are typically positioned on a gentle incline and rotate slowly, creating a continuous cascade of puffs inside the drum that exposes every surface area of each piece as they tumble forward. This mechanical tumbling is crucial. It ensures an even coating without crushing the fragile, aerated product. Inside the drum, two key applications occur almost simultaneously. First, a fine mist of oil is sprayed onto the hot puffs. Then, a controlled stream of seasoning powder is dispensed over the tumbling mass. The oil, which is typically a neutral vegetable oil like corn or canola, plays several roles in this step. Primarily, it acts as an adhesive layer that allows the seasoning powder to stick effectively to the puff's surface. Additionally, it helps activate the flavor compounds in the powder blend, carrying volatile aroma molecules and enhancing taste perception. The oil spray system uses ultra-fine atomizing nozzles that are precisely calibrated to deliver a uniform coat without oversaturation. Too much oil, and the puffs become greasy and soggy. Too little, and the powder won't adhere properly, leading to uneven seasoning distribution and flavorless bites. The timing, angle, and rate of oil application are closely monitored and adjusted by sensors and programmable logic controllers. Real-time feedback systems measure oil usage, droplet size, and the thermal signature of the puffs to ensure that coating is optimal under varying production speeds or ambient conditions. This level of automation ensures consistency across thousands of pounds of product produced per hour. As the puffs are coated in oil, the seasoning powder is introduced using a vibratory feeder or screw conveyor system. The powder is held in a hopper mounted above the flavor drum and is dispensed through controlled openings at a fixed rate, matched to the flow of puffs. The exact dosing rate depends on the type of Cheetos being produced. Flamin' Hot varieties require slightly more powder per unit than the traditional cheese puffs due to differences in density, powder, granularity, and flavor intensity. The seasoning blend itself is a complex formulation engineered not only for taste, but also for flow characteristics, adhesion, and shelf stability. The base of the powder is often dehydrated cheddar cheese, spray-dried into a fine particle form. This is combined with whey or whey protein concentrate, maltodextrin, salt, monosodium glutamate, MSG, disodium phosphate, citric acid, and natural or artificial flavors. Each of these ingredients plays a very specific role. Maltodextrin, for example, acts as a carrier and anti-caking agent that helps the powder distribute evenly and resist clumping. Citric acid provides a tangy bite that enhances cheese flavor. MSG boosts umami and deepens savory perception. Color additives like annatto or oleoresin paprika for classic cheese, and red 40 or yellow 6 for Flamin' Hot are oil dispersible pigments that give the snack its vivid appearance without creating spotting or streaks. The particle size distribution of the powder is engineered to align with the surface texture of the puffed snack. Powder that's too coarse will fall off, and powder that's too fine will clump or create an overly dusty texture. To prevent powder fallout, electrostatic systems are sometimes used in high-speed lines. In these cases, the powder is given a minor static charge to improve its affinity for the puff surface, minimizing waste and improving adhesion. Inside the flavor tumbler, the balance of oil spray and powder distribution creates a beautiful, uniform layer of seasoning that fully coats each puff without pooling at the bottom of the drum or leaving bald spots on the product. The drum's internal design is key. Angled baffles gently lift and drop the puffs to keep them moving without subjecting them to mechanical stress. As the snacks make their way to the end of the drum, they are now visually and sensorially transformed. Bright orange, evenly coated, and bursting with aroma. Once the seasoning phase is complete, the fully flavored Cheetos are gently transitioned to the final conveyor belt systems that lead to the packaging area. Here, another series of quality control measures come into play. Inline camera systems inspect color uniformity and powder coverage using advanced image recognition algorithms. If a section of the product stream is detected to have an irregular appearance, whether due to light seasoning, overcoating, or discoloration. It is flagged and diverted from the main line for manual inspection or disposal. At this point, the Cheetos are still vulnerable to moisture pickup, oxidation, and mechanical damage, so the packaging process must move swiftly and with precision. The conveyor system delivers the finished puffs to a multi-head weigher mounted above the bagging machines. This machine uses multiple weigh hoppers to rapidly measure exact product portions, typically in the range of 28 g to 250 g per serving, depending on the bag size. These weighers use real-time load cell feedback to select the optimal combination of buckets to match the target weight, within a tolerance as tight as +0. 2G. Each pre-measured portion is released down a chute into a vertical form-fill seal (VFFS) machine. These machines work by pulling a flat roll of pre-printed film through a collar that forms it into a tube. The bottom of the tube is heat sealed to create the first seam, the Cheetos are dropped in, and then the top is sealed and cut, simultaneously forming the bottom seal of the next bag in line. These machines can fill and seal over 100 bags per minute per lane, and multiple lanes often run in parallel for large-scale production. The film used for the packaging is multi-layered and engineered to provide barrier protection against light, oxygen, and moisture. It typically includes an outer polyester film for print quality and visual appeal, a middle layer of aluminum or metallized polypropylene for oxygen and light resistance, and an inner polyethylene layer for heat sealing and moisture resistance. As each bag is sealed, a date code, batch number, and factory identifier are printed using high-speed inkjet printers for traceability. Just after sealing, every bag passes through a series of checkpoints. Metal detectors scan for any foreign objects. Vision systems verify print alignment and code readability, and weight checkers ensure compliance with regulatory standards. Non-conforming bags are automatically ejected onto a rejection conveyor, where they are set aside for manual inspection. Approved bags are then grouped and packed into cardboard shipping cartons by robotic pick-and-place systems or automated drop packers. These cartons are sealed, barcoded, and routed to the palletizing station. Here, industrial robotic arms stack the cartons onto wooden or plastic pallets using optimized patterns for stability and load balance. As each pallet is completed, it is wrapped in stretch film to secure the load and protect it from dust and humidity during storage and transportation. The palletized loads are then scanned into the plant's warehouse management system, which tracks location, batch status, and distribution destination. Some pallets are moved to ambient storage if they are designated for short-haul routes, while others are transported to climate-controlled storage areas that maintain low humidity and consistent temperatures, ensuring that the product maintains its texture and flavor until it reaches its final destination. What follows is the outbound logistics phase, where the pallets are loaded onto trucks, routed to distribution centers, and delivered to retailers. But for now, every step inside the production facility, from the moment the cornmeal is hydrated to the final bag, passing the last inspection point, has been a meticulously engineered series of chemical, mechanical, and sensory transformations. Every component of the Cheetos production line is designed not just for efficiency and speed, but to deliver a reliably indulgent experience in every bag. And it all happens in a continuous, automated, high-output environment that must maintain exacting standards of quality, cleanliness, and consistency hour after hour, shift after shift. One of the key operational pillars at this stage is environmental control. Temperature, humidity, and airflow within the production zones are tightly monitored and controlled around the clock. Cheetos, especially after frying and seasoning, are highly sensitive to ambient conditions. If the air in the seasoning or packaging area carries too much humidity, for instance, the cheese powder may begin to clump, reducing its dispersibility and leading to uneven coating. Worse still, excess moisture can cause the puffs to begin absorbing water from the air, softening the texture and compromising the crisp, dry bite expected by consumers. To prevent these issues, HVAC systems specifically engineered for food processing environments are deployed throughout the Cheetos plant. These systems do more than just heat or cool. They dehumidify, filter, and exchange the air in sensitive zones at rapid intervals, ensuring a constant flow of purified, dry, temperature-stabilized air. Some areas, such as the seasoning tumblers or the vertical form-fill seal zone, may be isolated with positive air pressure to ensure that external air, dust, and contaminants do not seep into these critical zones. These environmental systems are integrated with digital controls that feed data into the facility's central monitoring hub. Temperature and humidity data are tracked every few seconds, and if any reading moves outside of pre-programmed tolerances, automatic alarms notify technicians to investigate immediately. In some cases, the system will even halt upstream processes automatically to prevent production under unsuitable conditions, protecting product quality. While environmental controls maintain external conditions, another system ensures the quality of what's happening on the line, inline quality assurance, and real-time analytics. Throughout the Cheetos line, from extrusion to bagging, dozens of sensors, scanners, and cameras work in unison to gather data on key quality metrics. These include moisture content, oil absorption rate, puff size, color uniformity, seasoning coverage, and weight per unit. Each of these factors contributes not only to taste and mouthfeel, but to customer satisfaction and regulatory compliance. Advanced laser micrometers and stereo imaging cameras measure the dimensions of each puff as it moves across the line at high speed. If puffs fall outside the programmed size range, either due to inconsistent extrusion pressure, die blockage, or improper cutting, those units are flagged and rejected automatically using pneumatic diverting arms. Simultaneously, optical sensors inspect the color of the fried puff to confirm it matches brand-specific targets. Color variation could indicate improper frying time, fluctuating oil temperature, or oil degradation. The system will trigger alerts or shut down sections of the line if it detects drift from acceptable limits. Another important part of inline quality is the metal detection system. Every snack must pass through high-sensitivity metal detectors or, in some cases, X-ray systems just before packaging. These devices scan for trace amounts of ferrous, non-ferrous, and stainless steel contaminants which could originate from worn machinery parts, upstream, or during maintenance. The sensitivity of these machines is such that they can detect metallic particles smaller than a millimeter in diameter. If a contaminated bag is identified, it is automatically ejected from the line, recorded in a digital log, and sent for root cause analysis. In high-output snack manufacturing, product changeovers are another critical concern. A single plant might produce multiple Cheetos variants: classic cheese, flamin' hot, jalapeno cheddar, and limited editions on the same line, sometimes switching several times per day. To avoid cross-contamination of flavor profiles and allergens, the factory must execute a full product changeover, which includes both physical and procedural steps. The final bags of one variant are run through the line until the seasoning and product types are completely cleared. Following that, dry cleaning and wipe-down protocols are enacted on exposed surfaces. In flavor tumbler zones and powder feeding systems, residue removal is handled by a combination of mechanical vacuums, compressed air nozzles, and in some cases, wet cleaning cycles. Pipes carrying seasoning powder are often disassembled and cleaned manually or flushed with air-driven pigs, foam or rubber projectiles that scrape the interior of the tube clean as they are propelled by compressed air. All cleaning steps are verified through ATP, adenosine triphosphate, swab tests, or allergen-specific strip tests to confirm the line is ready for the next product. Equipment cleaning and sanitization extend far beyond changeovers. Each section of the production line is scheduled for deep cleaning on a regular basis, with some components cleaned daily, others weekly, and critical systems like oil fryers undergoing monthly shutdowns for intensive maintenance. Every cleaning task is documented in a digital sanitation log that includes time-stamped photos, chemical usage records, technician ID, and verification by a supervisor. This log ensures compliance with food safety regulations and internal auditing systems. Speaking of oil fryers, one of the more maintenance-intensive systems in the Cheetos plant is the oil management setup. Used frying oil is constantly cycled through multi-stage filtration systems that remove fine particulates and oxidized residues. Inline sensors monitor oil color, free fatty acid content, and total polar compounds, all indicators of oil degradation. When thresholds are approached, fresh oil is introduced, and a portion of the old oil is purged to waste recovery tanks. This spent oil is not discarded haphazardly. Instead, it is captured and sent to third-party processors who refine it for use in biodiesel production or industrial lubricants, creating a closed-loop waste management process that supports sustainability goals. Seasoning systems have their own challenges in terms of dust and waste control. Cheese powder and spice blends are notoriously airborne, so extraction hoods fitted with HEPA filters are positioned above tumblers and conveyors to capture stray particles. These systems not only keep the air clean for workers, but also prevent buildup on surfaces and reduce cross-contamination risk. Powder recovered in this way is not reused in production, but is collected and weighed for waste tracking. Many factories monitor seasoning powder yield versus usage to optimize application and reduce excess without compromising flavor intensity. Additionally, factories employ floor-level waste segregation systems, where organic waste, such as broken puffs or overcooked batches, is separated from packaging materials and cleaning byproducts. Organic snack waste is often sent to animal feed processing plants or used in anaerobic digesters to generate energy, while plastics are compacted and shipped to recycling partners. These systems not only reduce landfill usage, but also lower the facility's total environmental impact per unit of product. Every phase of the factory's operation is governed by a robust system of documentation and auditing. Real-time production data is logged into the Manufacturing Execution System, MES, which connects to the plant's Enterprise Resource Planning, ERP, platform. This system allows plant managers to track every batch of Cheetos from cornmeal input to palletized output. If a quality issue is flagged post-distribution, every input, cornmeal batch, oil lot, seasoning blend, even the operator ID can be traced within seconds. This level of transparency is essential for large brands that operate under continuous scrutiny from regulators, retailers, and consumers alike. All these systems, from the air handlers and fryers to the conveyors and flavor blenders, are monitored by a central control room staffed by trained process engineers and operators. The control room acts as the nerve center of the factory. Touchscreen interfaces display real-time data on line performance, yield percentages, waste figures, and energy usage. Alarms and alerts notify the team of any deviation in pressure, temperature, fill levels, or machine health. The staff can make remote adjustments, schedule maintenance tasks, and even initiate partial or full shutdowns directly from their stations. In many facilities, predictive analytics platforms are integrated into these systems. Using machine learning algorithms, these platforms analyze historical and current data to forecast when a component might fail, how yield might shift under ambient changes, or what impact a change in oil temperature might have on puff expansion. This allows for proactive decision-making, reducing downtime and maximizing efficiency